Hey guys, welcome to the lecture on how to draw Lewis dot diagrams to visualize the formation of ionic compounds. Recall that anytime we want to visualize something going on at the microscopic level, it's often best to make a model or use a diagram. And that's why we learned how to draw Lewis dot diagrams for elements so that we could also use them to show the formation of compounds. So we're going to use these dot diagrams to show or visualize the transfer of electrons. And the reason why we're talking about a transfer of electrons here is because we're talking about ionic compounds. Okay, we will do this same sort of thing for covalent compounds as well, but it's not going to be a transfer of electrons. It's going to be a sharing of electrons. And remember, elements are doing this to get to a full valence shell to satisfy their octet rule. Okay, so for example number 1, let's do a compound that everybody is super familiar with, sodium chloride. Grab your periodic tables and find sodium on your periodic table. When you find sodium in group 1, you know that means that sodium has 1 valence electron. You also know, based on where sodium is on the periodic table, that sodium is a metal. Let's also draw chlorine, since chlorine is what the sodium is going to be bonding with. Find chlorine on the periodic table. Chlorine is in group 7, which means it has 7 valence electrons. And chlorine is a nonmetal. You guys already know, having studied the properties of metals and nonmetals, that metals react by losing their valence electrons. And a couple of you are asking, well, where does that electron go? In this case, it's going to the nonmetal. So sodium loses the electron and gives it away to chlorine, which of course then satisfies chlorine's octet. Chlorine had 7 valence electrons. Once it steals that one from sodium, now it will have 8. Sodium will also be satisfied because it lost its 1 valence electron and now has a full valence shell, 1 energy level down from that. At the end of this example, I'll show you the quantum mechanics so you can really visualize at a much deeper level what we're talking about here. Okay, so for simplicity's sake, metals lose valence electrons, nonmetals gain. Everybody's now satisfied. So the next step in our diagram would be to show the resulting charges. When sodium loses its 1 valence electron, it now has a 1 plus charge. When chlorine gains the valence electron, it now has a 1 minus charge. Of course, we can call these cations and anions. And you know that a 1 plus and a 1 minus will cancel each other out. In other words, these 2 atoms will come together to form a neutral, non-charged compound. And that compound is NaCl. Notice I did not write subscripts of 1. When I use 1 atom of the element, the 1 is understood in the writing of the formula. So this right here, this NaCl, is what we call the formula of the compound. So we can draw these Lewis dot structures, you guys, in 3 very distinct steps. Step number 1, draw your metal and your nonmetal with their valence electrons and show the transfer of those valence electrons in order to satisfy the octet rule. Then show the resulting charges. That is going to show us the electrostatic force that's going to hold this compound together, the 1 plus attracted to the 1 minus, resulting in the formula of the compound as NaCl. And we, of course, know the name of that is sodium chloride. Let's see if you guys can recognize a pattern in these names as we go on and do 2 more examples. Okay, let's get a little fancier this time. Let's work with, let's say, magnesium. Find magnesium on the periodic table. This is your metal. Notice I'm always doing my metal first and my non-metal second. Magnesium has 1, 2 valence electrons. Let's bond magnesium to fluorine. Fluorine is a halogen in group 7 with 7 valence electrons. And of course, this is a non-metal. So magnesium is going to lose valence electrons to fluorine. There we go. This fluorine atom is now satisfied. It is stable with 8 valence electrons once it gets one from the magnesium. But do you guys see how magnesium has not lost this second valence electron yet? Meaning this magnesium atom is not yet stable. It has not yet satisfied its octet rule. So in order to satisfy it, we need to bring in another fluorine. So these compounds can only form between one type of metal and one type of nonmetal. So I couldn't bring in a chlorine or something else. So I would need another fluorine atom with its 7 valence electrons. This electron can now be donated to that fluorine atom. And now do you see how everybody's satisfied? The magnesium got rid of both of its valence electrons to make a magnesium 2+ charge. And now I have 2 fluorines that have each gained one of those valence electrons. In other words, what I now have is a magnesium 2+ cation. It has a 2+ charge because it lost 2 valence electrons. I have 2 individual fluorine atoms, each with a 1- charge. So these are my anions. Notice again that the charges cancel out. The 2+ cancels with the 1- and the 1-. That's a total of a 2-, forming a stable compound between magnesium and fluorine. Now, in order to write the formula, we want to use subscripts to indicate how many of each atom we used. Magnesium, there was just 1 atom. It had a 2+ charge. For fluorine, we had 2 atoms. So we use a subscript of a 2 to represent the 2 fluorine anions. So this is my formula of my salt or my compound. And the name of this salt is magnesium fluoride. See the pattern? We'll talk about naming later on. Okay, let's do one more example. Let's get really annoying now. Let's make a compound between, I hope I left myself enough room for this nonsense. I'm going to start more in the middle here. Let's say calcium. Find calcium on the periodic table. You're going to find it in group number 2, which means 2 valence electrons. And of course, it is a metal. And let's bond that to phosphorus. Phosphorus is in group 5. 1, 2, 3, 4, 5. And this is a nonmetal. The metal is going to lose its valence electrons to the nonmetal to satisfy the octet rule. So there goes 1 valence electron, and there goes the other. Calcium is now stable, got rid of its 2 valence electrons, but the phosphorus is not. Still has an unpaired valence electron, so it only has a max right now of 7. It needs 8. So how do I satisfy that? I'm going to have to bring in another calcium with its 2 valence electrons. So the calcium will donate to the phosphorus. Now this phosphorus atom is satisfied, but this calcium is not. So how am I going to satisfy that? Let's bring in another phosphorus. Oh, maybe I shouldn't have started in the middle. Maybe I should have started over on the other side. I don't always think these things through before I do them. Calcium wants to get rid of that second valence electron. Boom. Going to go to the phosphorus. Ugh, oh no, this phosphorus isn't satisfied. It's a nonmetal. It needs to gain electrons. Where is it going to get them from? Let's bring in one more calcium with its 2 valence electrons. One of them can donate there, and one of them can donate there. And now I think it's finally all worked itself out. Do you see how I now have 3 calcium atoms that each donated 2 electrons? So if I was to draw those all as ions, I would have a calcium 2+, a calcium 2+, and a calcium 2+. I have 3 calciums, each with a 2+ charge. And I have 2 phosphorus atoms, each with a 3- charge. So these are remember, these are my cations. Over here, these are my anions. And I am canceling out my charges at a 6+ and a 6-. Okay, so step 1 shows all the transfer of the electrons. Step 2 is showing my resulting ions and their charges. Hopefully those charges now cancel out, and I'm left with a formula of Ca3P2. Again, your subscripts are showing how many of each ion makes up that compound. So this is my formula. And the name for this particular salt is calcium phosphide. Okay, now we are going to spend a lot more time in the days to come learning how to write these formulas and these names for ionic compounds. And the good news is that we don't actually have to do all of this work every single time in order to predict the formula and write the name. So stay tuned for how to write names and formulas for ionic compounds without having to draw Lewis dot diagrams. But I love Lewis dot diagrams because they really allow you to visualize what is happening with valence electrons. Now, if you're in honors chemistry, continue. If you're in CP, you can go ahead and give it a pause or stay tuned because you did learn about this as well, depending on how many of those optional lectures you came to last week. Okay, so I also wanted to explain or show you guys how we can use the quantum mechanical model of the atom to visualize what's happening here. So, Lewis dot structures are great, but I wanted you to know that you can also use those electron configurations that we spent all that time learning about to visualize what's happening as well. So, for example, let's take a look at the electron configurations for sodium and for chlorine and see if we can make sense of what's happening with the electrons in that model. But you know what? Before I do that, hang tight, you guys. I'm going to pause this recording and make myself a new screen. Be right back.